Our first speaker today is Wang from the Institute of Advanced Study. The title of her talk is Incidence Estimates with Application to Fourier Analysis, and her talk will be moderated by Shengwen. Take it away, Hong.
Okay. Thank you, Malabika, for the introduction. And I would like to thank the organizers for organizing this wonderful conference and for the opportunity to be able to speak here. Today, I'm going to talk about incidence estimates with application to Fourier analysis. And this includes joint work with Larry Guth, Noam Solomon, and with Larry Guth, Ciprian Demeter. So let's start with the classical incidence problem in combinatorics. Let L be a finite set of lines in RD. We are interested in the set of average points for this collection of lines. So here R is a number greater or equal to 2. So the set of average points for L is defined as the set of points P such that there are roughly R lines in L such that P lies in the line. And here by roughly R lines means that they are larger than say 10 over R and smaller than 10 times R. And when the dimension D is 2, we have the classical Ciprian-Demeter theorem. Which says that the number of average points for any set of lines L is bounded by a constant times L squared divided by R cubed plus L divided by R. This Ciprian-Demeter theorem is sharp for the following example. We look at the set of two parallel lines and then look at a set of equally spaced points, those red points. And our set of line L will be the set of all lines passing through two of those points. Now for any R between 2 and L to the 1/2, we can see that the number of, it's an exercise to show that the number of average points is roughly L squared divided by R cubed. And also the set of average points will lie between these two parallel lines here. And when this R is too large, when this R is greater than L to the 1/2, one can find the example like the following. We can pick L divided by R points and let the set of lines to be the lines passing through those R points. So here is the literature in some literature in the combinatoric setting of the incidence problem. Now we are going to discuss a continuous version. of this instance problem. Let T be the set of distinct tubes of length n and radius 1. So here by distinct, we mean that for any T1 and T2 in our set T, the intersection of T1 and T2 is smaller than 1/10. That has volume smaller than 1/10 of a tube. And we define the set of R-rich balls for T as the set of unit balls, disjoint unit balls. Q such that there are roughly R tubes in T and the intersection of Q and T is large. So here is our definition of R-rich unit balls. Before trying to prove any bound about the number of R-rich unit balls, let us look at 2 examples. So example 1. Example 1 is, as we might see, is the left-hand side, the picture on the left-hand side. We take a fat tube, TW, of length N and radius W, and then take the set T to be all distinct tubes inside this fat tube. Then one can check that the number of distinct tubes T contained in the fat tube is roughly W to the 2D minus 1. So here is in RD. And if we take R equals to W to the D minus 1, then the set of R-rich unit balls for our set of tubes is all disjoint unit balls lies inside all pairwise disjoint unit balls. That lies inside the fat tube. So now the number of R-rich unit balls is roughly W to the D minus 1 times N. So one can see that when W is very small compared to N, say N to the 1/100, then the number of R-rich unit balls is very large compared to the number of tubes. So in particular, it says that the above similarity-Trotter bound, we call it similarity-Trotter bound, does not hold for this example in the continuous case. Now let us look at the second example. example 2, we take all T is the set of all distinct tubes passing through a common point. Let's call this point O. Then the set of R-rich balls will be the set of all distinct unit balls. Lie in the annulus centered at O of radius roughly n times r to the minus 1 over d minus 1. And then the number of tubes is roughly n to the d minus 1. The number of R-rich unit balls is to the dth power. So the example 2 does not look as bad as example 1 in terms of the number of R-rich unit balls. But if we look at the particular case of d equals to 2, when d equals to 2, then n the number of tubes is n, and the number of R-rich balls is n squared over r squared. So this example still does not satisfy the semi-de-Chorter bound above, which is n squared divided by r cubed plus n divided by r. These two examples also illustrate that in general, if we want to have a good estimate about the number of R-rich balls in the continuous case, it is impossible. But those examples seem to be particular. And one may ask, if we rule out those examples, or if we impose some extra condition on the set of tubes, can we obtain better bounds? One might also ask, why are we interested on this question at all? So this incidence question is related to some well-known questions. For example, the Kakeya conjecture can be translated as an incidence problem. So the Kakeya conjecture says the following. If we take the set of tubes T to be the set of tubes such that there exists one tube in each 1 over r separated direction, Then what can we say about the number of average balls? The conjecture says that is bounded by n to the epsilon, where epsilon is an arbitrary small number greater than 0 times the number of tubes to the d over d minus 1 divided by r to the d over d minus 1. So in particular, the example 2 is an example that falls into the condition of the Kakeya conjecture. When we take all distinct tubes passing through a common point, one can check that there is exactly one tube in each 1 over n separated direction. And also this estimate the number of balls and tubes will just give this estimate, will just be an almost sharp example for this estimate. So even though the Kakeya conjecture seems a natural conjecture, it is important that it's also connected to another question in Fourier analysis that seems also natural. That is the restriction conjecture. So in Fourier analysis, we ask the following question: let f be a function such that the support of the Fourier transform of f is on the truncated paraboloid. Then we can, so we are interested in, we ask, how can we estimate the LP norm of f? To estimate the LP norm of f, we can decompose inside a large ball of radius r, for example. We can decompose f into sum over wave packets ft. So here, each ft, when we take absolute value, can be viewed as roughly a constant times the characteristics function of t. This modulus the tail, so as an intuition, we can think ft as a weight function times the characteristic function of t. And so in order to understand the LP norm of f, we need to understand how those wave packets interact. And to do so, we need to understand how the support of the wave packets, this T is a rescaled tube, how the support of the wave packets, which are the rescaled tubes, intersect. So this in turn translates into incidence problem. The above Kakeya conjecture is solved in dimension d equals to 2 and wide open in dimension d greater or equal to 3. So in dimension 3, the current best known bound is by S. Katz and Josh Zhao. And in higher dimensions, there is some written progress by Zhao and independently by Hickman, Rogers, and Zhang. In this today, we are not going to talk about any estimates regarding the Kakeya conjecture. We just want to state this conjecture as and this as conjectured bound as comparison to the estimate that we are going to discuss later. So even though a Kakeya conjecture is very hard, if we impose some condition, then we will have some estimate. For example, if in dimension 2, when d equals to 2, if we impose the bilinear condition, which says that for any average balls and most of the pairs of tubes passing through Q, the angle between T1 and T2 is larger than a constant times 1, which is on the picture is here on the right hand side. So we call this the bilinear condition. Then in dimension 2, we can show that the number of average balls is bounded by t squared divided by r squared. This estimate is actually easy to show because when the interesting tubes intersect, they intersect at an angle larger than 1. So morally speaking, 2 tubes intersect at roughly only 1 unit balls. That explains why the number of average balls is bounded by t squared divided by r squared. So for a long time, this bilinear estimate in R2 seems like the best we can do. Sorry. So for a long time, this seems like the best estimate we can do. One may ask, can we do better when the set of tubes are in some special configuration? So now we are ready to introduce our result. Theorem A says that in R2, let S be a parameter between 1 and n, and let T be a set of tubes. Then we define NS as the maximum number of tubes in T that are contained in an S times n rectangle. Then we have the following estimate: R squared times the number of average unit balls is smaller than sum over all dyadic S between 1 and n, and then n as divided by S times the number of tubes T times n, the length of tube, and then times delta S. So this delta S takes value 0 or 1 that we'll discuss later when it takes value 0 and when it takes value 1. But for now, let's just ignore this delta S term and look at the whole estimate. So maybe it's a good point to pause and just stare at this estimate. I saw there are some chats. Okay, it seems that all the questions have been answered. Great. So now we look at this complicated looking estimate. First of all, there is the parameter ns. So when s equals to 1, n1 will just be 1. When s equals to capital N, the length of the tube, and capital N, here if we assume that all tubes lie in a ball of radius n, then n capital N will be roughly the number of tubes, because we are interested in when all tubes are lying in a ball of radius n. Otherwise, we will have some, say, better estimate. This parameter ns measures how clustered the tubes are. In particular, if we look at the example 1, when all tubes are contained in a fat tube here. In this example, the ns, we can take s to be w here. The ns will be very large. And then one can interpret this estimate as follows. If we can either identify an S such that the tubes are clustered into fat tubes of radius S. Otherwise, we would otherwise we'll have some good estimate. So the second comment is that Theorem A does not require bilinear assumption. So in particular, the example 1 falls into where all the tubes are lie in the fat tube, falls into the statement, the range of Theorem A. Now we are ready to say what delta S is. So delta S equals to 1 if for a typical square QS of side length S, the number of tubes in T passing through QS is larger than R times S. Otherwise, delta S takes the value 0. So here we can call this a pointwise bound. Pointwise condition. Sorry, here if for typical square QS set length S and QS contains a point, a unit ball Q in a unit ball Q in PRT. So in this example, like if this is a unit ball Q in the a unit ball Q in the PRT, RH unit balls, then QS is the square of set length S containing this Q, and then we count how many tubes in T that passing through it. The function delta S takes value of 1 only if for most of those Q, the flattened square QS contains more than R times S number of tubes passing through QS. Otherwise, this delta S will be 0. To better digest this delta S, we will look at when S equals to capital N. This, the right-hand side will become T square divided by N and times N. So this will cancel out, and times the delta S. But remember that we take value 1 only if this condition holds, which means that here the left-hand side will become all the tubes T, which implies that T should be bigger than R times N. But this condition says that when R is smaller than T divided by N, then it says that roughly speaking, we can randomly put the tubes. We can put the tubes in a random position, and then for a typical point in the square, we would have more than T divided by N many tubes passing through it. So this delta N equals to 1 is a very strong condition on the R, which says that the R rich unit balls, this parameter R is as small as possible, but this rarely happens. So in general, the delta N equals to 1 does not happen unless we have this very strong condition on R. And in this case, we cannot hope to have anything better than that. So I hope I have explained this estimate clearly. And now, even though the statement of Theorem A looks complicated, the proof is actually not as complicated as the statement. So now we explain the proof ideas of Theorem A. we take G to be sum of phi t over all tubes in T, and each phi t is a smooth bump function. On T. Then the left-hand side of the inequality, R squared times the number of average unit balls, will be bounded by the integral of G squared. So here we integrate over the set of average unit balls. We will use this notation to denote the union of the unit balls in PRT. And then by Pointreal, this is bounded by the Fourier transform of G, the L2 norm of the Fourier transform of G. So our next step is to study the Fourier transform of G. So since the Fourier transform of G is the sum over the Fourier transform of phi t hat, the Fourier transform of phi t, we start by studying phi t hat. So for each t of length n and width 1, since phi t is just a bump function on T by the uncertainty principle or stationary phase, phi t hat is essentially supported on the dual convex T star of T. I recall that the dual convex is defined as the set of X such that X times Y minus the center of T. Ct is the center of T. It's bounded by 1. So in this picture, when T is this, then T star is a thin rectangle of length 1 and radius 1 over n that points on the orthogonal direction of T. And also each T star passes through the origin. So now G hat is essentially supported on the union of those different T stars that passing through the origin. Then we can decompose the support of G hat, the essential support of G hat, into different frequencies. We decompose into frequencies with norm about S3 minus 1. So this S, as we might guess, takes value from 1 to n, and that is closely related to the S that appeared in the formula here. We can define GS as the restriction of G on frequencies about S to the minus 1. So this phi W, absolute value of W about S to the minus 1 is a bump function supported on the frequency space that's lies on the annulus of radius about s to the minus 1. Then if G is bounded by GS, on most unit balls in PRT, in the set of average unit balls, then it's an exercise for one to check that the pointwise bound holds, condition holds. Recall that the pointwise bound condition is given here when we discuss when the value delta S takes, when delta S takes value 1. For the rest of the argument, different frequencies are, the argument for different frequencies is roughly similar. So we will focus on the highest frequency and leave the rest to the audience. So if G is bounded by G1, the highest frequency, then we define theta as the part of T star that's outside of the ball of radius, say 1/2. So this is theta. Sorry. I see a question about this is a rare case, isn't it, for the first if. So for this if, we said that the rare case is when S is equals to N, which corresponds, when we refer to the proof, is when G is dominated by the lowest frequency, which is the frequency with norm below 1/n. And I guess this rarely happens, yes. But for other frequencies, it depends on the structure of T. So now let's continue the proof for the highest frequency. For each theta, we define G theta as sum over the phi t such that theta is contained in T star. So recall that theta is this rectangle, the part of T star that outside of a ball of radius 1/2. Then here, when we look at the G theta, here all the T in this summation are parallel. Those T parallel to theta dual. Well, theta dual is the dual convex of theta, with the dual having the same definition here. So now we continue the proof by the L2 orthogonality. G1 square is bounded by sum over theta, G theta. And for each theta, since the tubes are parallel, by our assumption that the tubes are distinct, we know that we can also, this is also bounded by sum over phi t squared for different t. And this is about number of tubes t times the volume of a tube, which is n. So this gives the first term on this formula when s equals to 1 and s is 1, and we have t times n. Now we have described all the proof idea of theorem A. And there are a few comments after the proof. First of all, we can see that the estimate makes more sense when the number of tubes is larger than n, because we have a term, a factor of n on the right-hand side anyways. When the number of tubes is smaller than n, sometimes, most of the time, using the bilinear estimate is better. And also this, the reason why n appears is related to this inequality. When the number of tubes is too small, this inequality will be a big loss, because this inequality includes not only those R-rich unit balls, but also includes those, say, the unit balls that might not have other tubes intersecting it. So the question is, how about when the number of tubes is smaller than n? Can we do anything better than the bilinear estimate? So another question is that this proof, if we repeat the whole proof for higher dimensions, we can have some estimate. But this estimate usually is not so good. The reason is that in higher dimensions, when we consider T star, here in 2 dimensions, the T star is a tube, is a dual rectangle. But in higher dimensions, the T star will become a plate. And it's harder to identify those theta that has some orthogonality property in higher dimensions, because 2 different plates, they intersect a lot, even when the frequency is large. But here, the 2 different T star, when the frequency is large, they do not really intersect. So another question is higher dimensions. Even if this method in higher dimension does not work so well, but it works particularly well in 1 dimension. So one can also use this technique to study other objects whose direction is 1-dimensional. Can use to study, for example, a function f whose Fourier transform is supported on the cone in R3. So this one can see the work with Guth and Zhang. Myself and on the square function estimate. Okay, now I see the time is up, so I think I will stop here. Thank you for your attention.